Well, hello everybody. Glad to see folks are on. Give a thumbs up if you're here, just so I know who's here. That'd be good to see. We're looking at an exam coming up, so let's get right to the questions if you have them. Let's see. I do have scheduled for that the exam is supposed to be today, starting out today anyway, and go through. Let's see, what did we say it was going to be through? I think I said through Friday, right? Let me check. Make sure that I'm doing what I'm saying here. Nope, it says, till Thursday. So it'll be open today, and we'll finish it up then on Thursday. So we're going to have our usual 2-hour time limit like we did on the last exam, and same format. Hey, Dick, good to see you. Let's see. He's asking a question about whether I received an email from homework. I don't. Hey, Chase. I don't remember seeing it, but if you could remind me what it was about, then I will answer your question, I guess, on it. Was it recent? Was it about homework that was due last week, or what? I'm not sure what it was about. So I have answered a bunch of emails, but I don't remember that one specifically. So if you could give me a little bit of a hint about what it was about, then maybe I could remember if I dealt with it. But anyway, let's see. So, and I don't. So just to make sure I'm getting the questions here in answer, Dickie, I don't think I got your email, but I might have missed it because I've got a whole bunch that I've been looking through for a bunch of different things. I get a number of them a day, so if I missed it, I'm sorry. So if you would just if you have a question about it here, then I can answer it. Otherwise, you can resend it, and I'll check it this afternoon once I have a chance to. Once we finish the stream and stuff like that, I'll check on that. So yeah, sorry about that if I missed your email. Sammy said, for the lab, I plotted the voltage on the x-axis and the current on the y-axis, but got a straight line. When I did it the other way, I got a line with a slope. I guess I don't understand either way you get a line with a slope to some extent. I want to make sure I understand what you mean. So like if you plotted, that's not exactly straight, I guess. So you're saying plotted the voltage on the x-axis, okay, and then you plotted the current on the y-axis, and you got a straight line. Now, by a straight line, you mean a purely horizontal line? Or do you mean a line that's a straight line like that, like the slope doesn't change? Because either way, even if you were to switch that and have it plotted like that, you get a straight line, but maybe with a different slope. So I don't know exactly what you mean by that, Sammy. Do you mean you got a horizontal line for that? Okay, thanks, Dickie. I'll check into it once the stream is done. So I don't know. I guess I have to be careful how I ask questions here because Sammy just said yes, but I guess I asked 2 questions, so I'm not sure which one you're answering to. So if you could just specify whether I got a horizontal line for this first plot or something like that. Okay, you got a horizontal line. Okay, that would be an interesting, by interesting I mean a result which would be really hard to analyze. So what you're saying is that you got a purely horizontal line. Now, there's a bit of a problem with this. Now, you'll notice it would mean that you got the same current for every voltage that you applied to it. And hopefully you didn't get that. Like when you turn the... Okay. So that would mean, hopefully when you turn up the voltage, you got different values of the current. Like when you turn up the voltage, the current went up, hopefully. What it could mean, it's possible, there's a couple of things that you could have done. So if you were looking at the situation where you had if you're using Excel, make sure that you're actually plotting the current versus the voltage and not the current versus the cell number of the voltage, because that's that could give you a weird, or the current or the voltage and then you apply to the cell number of the current, because that could give rise to a little bit of funkiness there. So just check to make sure that it's plotting what you think it's plotting. The other thing that it could be, if you got a line that appears to be horizontal, is that the slope is really, really small. So make sure that the scale that you're using here for the current, or the scale that you're using for the voltage, is appropriate, so that you're not just because then you would see no slope. That would be another thing that could potentially cause a problem. So I would say check to make sure you're plotting what you think you're plotting, and that the scale is zoomed in enough or zoomed out enough, depending on whether you're talking about the y-axis or x-axis. Make sure that the scale is appropriate so that you can actually see the detail of the increase or the decrease or whatever it is. Those are the only things that I can think of. Because when I messed around with it and did the lab with it, I had currents which were, as the voltage varied, the current went up linearly without a not constant slope. Okay, so sorry if you've exhausted those things on it, Sammy, but just I would check. You can still go back into the Tinkercad thing, and you can check, like if you put a 100 ohm resistor in there, for instance, and you turn the little knob on the voltage. When the voltage goes up, look at what the ammeter says. If the ammeter also goes up, then it can't be horizontal. That you shouldn't be seeing a horizontal line here, because that would mean the current is the same for every voltage that you picked if it was purely horizontal. So just make sure that you're plotting it right, or you're entering it right, or something like that. It sounds like a really small hiccup. It doesn't sound like something major, but it sounds like something which seems confusing, but I can't quite tell what would be causing that. I guess I'll throw this out there to other folks. If other folks are having the same problem with that first plot as Sammy is, could you just let me know in the chat? The other thing that I wanted to mention as I wait for the questions to roll in, so we don't have too much downtime here, is the other thing I wanted to mention is that my apologies on on not having your Lab 7 assignment up. I didn't notice it until yesterday. That I didn't have an assignment actually up to receive the lab reports that you've been working on over the past week since we've been doing our Tinkercad lab. So I made that available last night, and you should be able to get it in on time. If folks didn't check in or something like that, I can extend the time limit on the lab a little bit, maybe another day or so. So just please let me know if there was trouble with that somehow, so that we make sure and get those in. But you should be able to attach a Word document to your assignment, and then I'll go ahead and grade those labs that you did from last week. Let's see. I'm not sure who Elliot Time is, but I don't understand the question. 300 by 40,902. I don't understand what that is exactly. If you could be a little bit more clear about that, if you're a member of the class, just please feel free to clarify that if you can. Were there other questions from the class about what's going on for the next couple of days here with regard to the exam which is coming up, or labs? Any one of those things is fine. So just and again, don't hesitate to just pull in pop your questions into the chat so that I can answer them as we go through. But I do want to mention that about what we're doing, just as an overview of what our class, or what the exam is going to cover. So the exam is covering chapters 25, 26, and 27. These are the chapters on specifically capacitance and dielectrics. Chapter 26 is the chapter on current, the definition of Ohm's law, and the calculation of resistance, the relationship between current and resistance. And then we also talked about electrical power, the rate at which energy is consumed in a circuit. P is equal to IV. And because the units are all what we've been using basic units, like the volt is the joule per coulomb, and an amp is a coulomb per second. The unit of power will be joules per second, which is a watt, the same thing as we're used to. It's the wattage of the metric system. And then the last chapter that we're covering here in this exam, starting a little bit later today, is the section on DC circuits and combinations of resistors and things like that. So that is the topic of chapter 27. Chapter 27 therefore includes ideas like Kirchoff's rules, the loop rule and the junction rule, so you should know how to apply those. It also includes RC circuits. So those things can be looked at too. So Zach just had a question. Could you do a capacitor with a dielectric problem? Sure, we could do something like that. So let's say that I have, let's say that I'm building let's build a capacitor. Let's say it's a parallel plate capacitor, and let's specify all the dimensions, and that there's a dielectric between them or something like that. So I'm going to make one up here on the fly. I'm going to have to do some Googling off screen. Oh, it's on the screen. But I'll do some Googling as we go here to figure out what some things are. So let's see. Let's say that I have, with the dimensions we're talking about here are such that I've got a parallel plate capacitor. Oops, we have to have a brush. All right, here we go. So I have a parallel plate capacitor, and both plates are going to be identical. Okay, and the dimensions of the plate are, let's say that this plate is, let's say that's 5 centimeters on this side, and it's 10 centimeters on this side. And then there's a brick of dielectric that fits inside of this. And then there's another plate that's identical underneath it. Alright, so I guess there's our, alright, so here's our other plate. So the other plate sits underneath here, and let's say that this thickness here, so this is not to scale, I'm going to say that that thickness right there is, what do you want to call it? Let's call it 2 millimeters. Let's go 2.0 millimeters. And this dielectric right here, it's a solid piece of dielectric. Let's say that dielectric is paraffin. Okay, so that's a pretty, it's like paraffin wax or something like that. Because I think I can find what the dielectric constant that is. So what we're going to do is we're going to find the capacitance of this. So what we're going to do is we're going to say that the capacitance of this device is going to be, and I don't make very good kappas, but here's a kappa. It's the kappa for paraffin, which we're going to have to look up. And that's going to, and since this is a parallel plate capacitor, the capacitance of it without the dielectric would be the area times epsilon naught divided by the separation between the plates. Okay, and we're going to want those separation, all these distances and all these units and all those sorts of things. We're going to want them in units of meters, so that everything is in MKS units. So I'm not gonna pause right now, but I'm gonna ask Zach the question to be sure that this is, if this is okay, if you'd rather see something slightly different than this, then let me know in the chat. I will finish this problem, and then we can do another one that's more to your liking. So if you want to, if this is not what you expected, this sort of calculation is not what you expected, go ahead and specify further what you would rather have seen. So here's what we're going to do. So while I sort of wait for that, and I finish out this problem as I wait for Zach's response, let's look up what the dielectric constant of paraffin is. So I've got, let's see, I got the book sitting here in front of me, chapter 25. I'm going to check. Okay, thanks. If that looks good, then we'll just continue with that. So here's what we'll do. I'm looking at so on page 677 of the book, there is a bunch of stuff. Oh, there we go. So paraffin impregnated paper. I'm going to go with that. We're going to call it paraffin impregnated paper. Okay, it says this is the approximate dielectric constants and dielectric strengths of various materials at room temperature. So I'm going to say this is paraffin impregnated paper. Okay, it says that the dielectric constant is 3.5. Okay. And the dielectric constant is just a dimensionless number. It does not have any, it just says by what factor the capacitance is going to be enhanced, or alternatively, the other way to put it is it would be the factor by which the electric field and the voltage get reduced. So this is going to enhance the capacitance by a factor of 3.5. That's what the dielectric constant does. Or alternatively, you could say if I applied a voltage to that, those two plates, it would say that the electric field, if you put the paraffin in there, is 3.5 times smaller. It's 1 over 3.5 times its original value. So now we need the area here. We're going to put that this is 0.02 meters. That's 2 centimeters. Times 0.05 meters. So that's the area of this thing. So there's area in square meters now, and then we're going to put the permittivity of free space in there. That's again sort of a lookup thing, and it's 8. I'm probably going to run out of space here, but you get the 8.85 times 10 to the negative 11th or 12th. I can't remember. I'll look this up in the book too. It's on the inside front cover of the book, which I grab it. Here it is. Permittivity of free space. Negative 12th. Negative 12th. All right, to the negative 12. And I don't have the units of this are, let's see, I think it's Newton meters squared, or no, Coulomb squared per Newton meter squared. All right, so the units behind that would be Coulomb squared per Newton meter squared. And then I'd have to divide by the separation between the two plates. That's 2 millimeters. 0.002 meters. So everything's in meters there, and then I can plug this in. Okay, so this has a capacitance of 3.5 times 0.02 times 0.05. This is not going to have very big capacitance, obviously. Times 8.85 times 10 to the minus 12, so I plug that in, and divide by 0.002. And I get a capacitance of 1.55. 1.55 times 10 to the negative 11. It's a really small capacitance, negative 11. And then the units of this would actually be in farads. Capital F, named after Michael Faraday, but they abbreviate it to farads. So if you look at this, this is like, let's see, Coulomb squared per Newton meter. And by the way, the C is of Coulomb. So let's see, what would we have here? We would have meter squared, we'd have Coulomb squared per Newton meter, or something like that, would be the unit of capacitance. Okay. Does that make sense? So that's one where we calculate the capacitance if we have a dielectric in it. The dielectric enhances the capacitance by a factor of kappa. Kappa being that dimensionless constant that tells us how much better the capacitor is because it has a dielectric. I do want to mention also, if you happen to be looking, so sort of doing a little bit of filler here, but a little bit extra context. Again, please feel free to ask questions as we make our way through here. So don't wait for me to call for questions. Just put them in the chat. I'll get to them eventually if I'm waiting. So there's another column in the book in that table on page 677. This is table 25.1. The table lists there two things for a bunch of different materials. It lists the dielectric constant kappa, and it also lists what they call the dielectric strength. Now, what does that mean? What is the dielectric strength? The dielectric strength tells you the amount of electric field that this material can experience and still remain an insulator. If the electric field, because of the presence of a voltage or something like that being applied to this, if the electric field in this material within this material gets too strong, eventually the electrons, because of the really, really strong electric field, they will be torn off of their individual parent atoms or the material with that individually. It'll tear the electrons off and they'll move. In other words, what was an insulator will become a conductor if you push hard enough with a big enough field. That tells you, that dielectric strength tells you how strong of a field that particular material can stand and still remain an insulator. Any field bigger than that will cause what we call dielectric breakdown. It will cause the material to become basically a conductor. All right, so Ghost House 88 says, could we do a problem that involves a junction rule and loop rule, like 2720 or 2721? We sure can. All right, so let's have a look here at what those are. So let me just remind myself what 20 and 21 look like. Yep, you bet. All right, plenty of fun stuff there. You bet. Let's talk about that one, because that's really a huge culmination of what we do, is the ability to analyze these circuits like that. So let's have a look at that. I will clear this one out too, so we have plenty of space. And let's do a junction or loop rule style problem. So let's say that I have let's draw a circuit here, and then we're going to perform the analysis on it. And I will say also that I am not particularly too worried about the solution using algebra just yet. So all I'm going to do is set up the problem, and then I'll leave it. I'll basically stop at that point and say, and then we could just go on and solve for the currents from the algebra here. So this is what we'll do. Let's say that I've got a 5-volt battery right here. Okay, and then what I have is I've got a resistor here, which is, I'm going to call this 10 ohms. Okay, and this resistor then is attached. Let's say that there is another battery here. And in addition, behind that battery, there's another resistor here, which will be 5 ohms. It's supposed to be a 5. And let's say that this voltage right here is 7 volts. Okay, and then what I'm going to have over here is there's going to be one resistor, which that one would be 6 ohms. And then behind that resistor, there's yet another resistor of 3 ohms. And then it gets attached over here and it goes to the spot and closes. So their circuit is relatively complicated. It's got a couple of batteries, it's got 4 different resistors, and all that sort of stuff. So this is the kind of problem, let's say, that we wanted to solve. And usually what happens at this stage, once we got this, the question will be, if I wanted to make it sort of kind of comprehensive, what I might do is I might ask, what is the power dissipated by each of the resistors in the circuit, the 10, the 5, the 6, and the 3 ohm resistors? How much power gets dissipated in each of them? And it's dissipated because as the charges flow through the resistor, they encounter resistance, which bumps them into the atoms. We talked about that back in the back a couple of weeks ago now. And when they do, they bump into the atoms and they give up their energy to the atoms, and the atoms start bouncing around and wiggling around, and that's what heats up the resistor. So the resistor consumes power at a rate which is equal to P is equal to IV. So the power that is consumed by any resistor will be equal to the current flowing through the resistor times the voltage difference across the resistor. Another way to calculate that also would be using that V is equal to IR, which means I could rearrange that formula so it looks like this. It's I squared times the resistance. So then all you would need to do then is ask yourself, well, how much current is flowing through each resistor? If I knew that, then I could square that current in amps, multiply times the resistance that has that current flowing through it, and that would be the power, that's dissipated in that resistor. Do it for each resistor in question, and I've got the total power that is being dissipated in each one. So that's sort of one thing that you have to do. So that means that I would have to calculate the current that flows through each of the resistors. All right, well, this is what I'm going to do now. Remember, the first stage in any problem like this is labeling our current. So this is what I'm going to do. I'm going to say that this current right here, there's a current that flows this way. I'm going to guess that current flows this way, and I'm going to call it I1. Because why not? I got to label it something. And then I've got a current that flows in this branch of the circuit. Notice how there's a junction right here. So there's a current that flows here. And I guess I'm not quite sure. So this is what I'm going to do. I'm going to say that this current here, just going to make it could flow either way. I'm not sure which way it's going to go. Because notice this is 7 volts and that's 5 volts. So you might think, well, maybe this current flows this way instead of that way. But there'll be current that flows through this one, which is going to reduce the difference in voltage from here to here. So maybe this voltage is still lower than 5 volts over here. So it's really hard to tell which one it's going to be. So I just would say, all right, well, let's just guess. I'm going to guess that the current flows down. Maybe wrong, maybe right, but I'm going to call it I2 because I got to distinguish it from that one. And then I've got a current that flows in this branch as well, which is going to be I3. And I know that I3 is the current that goes through this 6 ohm resistor, but since they're in series, I know that the current through this resistor and this resistor are the same. And the current that flows out of this branch goes back through the battery, and, at least the way that I've guessed its current is going to go, it's also going to flow through this 5 ohm resistor in that way. And then I got the current that flows here. I'm saying that one's flowing through the 10 ohm resistor, and that's the one that flows out of the battery. So that's the way I've got it labeled. Okay, and those are the only 3 currents that really exist here. There's this branch's current, that's I3. There's this branch's current in here, which is I2. And there's this branch's current, which is I1, because no spot in here has a current which is different because there's no way for it to branch. Everything here is in series with everything in that particular branch. All right, so here's what we're going to do. We're going to analyze this circuit using Kirchoff's rules. And the way to approach this is you've got to pick 2 loops and 1 junction. Okay, you can pick any one you want. So this is what I'm going to do. I'm going to pick the first loop that I'm going to pick. I'm going to pick this one. It's going to start here. It's going to go around this way. That is the way I'm going to choose for this particular circuit to circulate. Now, it doesn't have to be the way the current flows. I could pick any one I want, but I'm going to pick this loop right here. So this is what I'm going to do. I'm going to start back here, down here at this bottom spot right here, and I'm going to make a loop that goes all the way around here and returns to that spot. So the first thing, I'm going to cross this resistor, and notice that I'm crossing this 5 ohm resistor opposite the direction the current is flowing. So that actually is supposed to represent an increase in the voltage. So that would be I2, I got the plus sign there. I got I2 times 5 ohms. Okay, so there's a rise in voltage going from there to there. It's a guess. If I2 is actually traveling this way, it would be minus. But I'm going from here to here. That's a rise in voltage. As I go from here to here, I gain 7 volts because I go from the negative terminal of the battery to the positive terminal of the battery in my motion going up here from this junction towards that one. Okay, so there we go. Plus 7 volts for that. Now, I'm going to continue. Nothing happens here, nothing happens here until I get to this spot right here where I'm crossing the 6 ohm resistor. Notice I am crossing the 6 ohm resistor in the same direction that the current is flowing. So that does represent a drop in voltage equal to, according to Ohm's law again, I times R. In this case, it's I3 times the 6 ohm resistor. Okay, then after I get done crossing the 6 ohm resistor, I cross the 3 ohm resistor as well. Same current, different resistor. It's the 3 ohm resistor that's involved here. And then I cross this horizontal line down here to get back to where I started, and there's nothing that happens in there. So I get some of the rises, some of the drops have to add up to 0. So that's my first loop. Now I want you to notice something here. These two resistors are in series with one another. Since they're in series with one another, notice what I could do. They have this common factor of I3 because series means they have this common current. I could just say I3 times 9 ohms there, couldn't I? Because I could just combine these two. They both have the common factor of I3. I could factor out the I3 and have 6 ohms plus 3 ohms there. So you could just combine the two resistors. But remember, if my problem is asking for the power dissipated through each resistor, there's a 6 ohm resistor and there's a 3 ohm resistor. There's not a 9 ohm resistor in this thing, so you'd have to, separate it out later anyway. But we're just looking for the currents at this stage, so it wouldn't really hurt us to combine those if we wanted to, which we kind of will anyway. So that's one loop. Let's do another loop. Okay, well, another loop would be the loop that starts here. And let's say that it includes this loop here. Let's say that it does. Okay, this spot here. So I'm going to go all the way around here through the 10 ohm resistor, turn down this branch right here, go through the battery, go through the 5 ohm resistor, then turn at this branch again and come back to where I started. So that branch is going to have, if I go from here to here, I increase my voltage by 5 volts. Then I'm going in the direction of the current. The current is I1. So I do I1 times what resistance? 10 ohms. So this is V is equal to IR. Again. All right, so we got there. Now we're at this point right here. We're going to turn into this part to make our loop. We could have just as easily gone through here and it would have done the same thing, but we decided this is the loop we wanted to do. Okay, so we then lose 7 volts. Then we gain, because remember again, we're going to lose. Sorry, we're going to lose. We don't gain, we lose. Okay, back to this. We actually are going in the direction of the current here for this one. So we do minus I2 times the 5 ohm resistance. V is equal to IR again. Okay, so we've gone through that one. And now I'm back to this spot here, and there's no change from there to there because there's no device in here, just a wire. So there, we're done. That's our second loop. Now, the third loop wouldn't give us any more information here. We could choose, say, this big loop right here, but since this is in parallel with this, that is just going to give the same thing as that. So it's no new information. What we need to do instead is use the junction rule here at this spot up here to find our third condition. So remember the sum of the currents that go into the loop. So the only current that goes into this loop as we see it is I1. And then the currents that flow away from it are I2 plus I3. And there we go. Now notice what we've done is we've generated 3 equations and 3 unknowns. The three equations are here, here, and here. Two loops, one junction. And the three unknowns are I1, I2, and I3. And then it would just be a matter of solving algebraically these three equations for I1, I2, and I3 using any old algebraic techniques that you want. Getting it ready for, all right, are there any questions on that? So that's really what I want you to be able to do. This is 8 out of 10 points would be labeling your circuits. If you don't label your currents in your circuit somehow, then I can't know what you're talking about. So what I would like you to do on exams when you do this, because I know it's really practically impossible to actually write something, but I want you to type it out. So basically you would say, you could say something like, at the junction between the junction at the top, because I would have labels or something like that and the pictures associated with it. The junction at the top, current 1 is traveling through the 10 ohm resistor towards the junction. I3 travels away from the junction to the 6 and 3 ohm resistors, and I2 travels down away from the junction through the 7 volt battery and the 5 ohm resistor. So that would specify to me what you mean by the directions of each of the currents. So you would have set those up. Okay? So when you're solving the problem, of course, you should probably write it on a piece of paper so you do your algebra, and then when you're entering it, the first thing that you should enter in that little text box is, this is the way each of my currents are going and how I'm labeling them. Because you could have labeled this one I1 and this one I3 and this one I2 or something like that. Just tell me which one is which so I know what you're talking about and which way they're traveling relative to the various junctions. Okay? But this is if once you do this, once you got those labels and the correct three equations, and there's a couple of different ones you could do here, but as long as you got a set of equations that are correct, that's 80% of the points. The last 20% of the points will be, can they solve the algebra? And again, I would have mentioned before is I will create a situation, create problems, so that the algebra will be relatively simple. So those last 2 points, you're not going to have to lift the world with your mathematical skills or anything like that. It's just going to be, the algebra should be relatively simple. Is that good? Did that answer your question? Is that okay? Yes, that is correct. So the question in the chat is that, is the reason why the voltage in the circuit equal to 0 is due to the conservation of energy? Yes, that is true. The way that one way you might think about it is like this. Imagine I had, okay, I'm glad that the problem answered your question was helpful. And let's just talk about that second question that you had about conservation of energy. Let's imagine that there's a little positive charge right here, and it travels around this loop. Okay? One thing that you notice is if you were to put a volt or a current meter, an ammeter in this circuit, you would see that this charge right here, that the current in this branch of the loop is whatever current we get there. It's like 3 amps or something like that. Okay, let's say it's 3 amps. Probably isn't, but let's just say it is. Okay, it's 3 amps. It's 3 amps here, it's 3 amps here. Now, I want you to think about that. If there was a positive charge that started out here and actually traveled through the battery, through this resistor, went down through this battery, went through this resistor, and got here, back here again, if the voltage that it received there was positive, that would mean that the electrical potential energy of this thing went up. In other words, it has electrical potential energy that increases as it goes around the loop. Now, if you could do that, if that happened, that means that this charged particle would go fast, would gain energy the whole time, and it would speed up and speed up and speed up and speed up without bound forever. It would just continue that circulation. Every time it would keep going around that loop, and every time it went around the loop, it'd go faster. And you think what that would mean? It means that the energy of that little charged particle would grow without bound. Just say, well, how many times do you want to go around the loop? Every time you gain 5 joules. And then after you went around again, now you've gained 10 joules from where you started. And then go around again. Now I'm at 15 joules. You just keep gaining energy the whole time. That's why conservation of energy says the overall voltage rise and the voltage drops have to be equal to 0. Otherwise, the charge would just accelerate without any upper limit. It would just go forever. And that's why we know that the voltage rises and the voltage drops have to sum up to 0. Any other questions that I can answer about anything that we're talking about here? Sorry if I've got to kind of, I'm getting a little bit hoarse because I had another live stream earlier today for my modern physics class, so I'm already did a lot of talking. So any other questions I got? Now we got a decent number of viewers here. Did anybody have questions on RC circuits or charging capacitors or basic ideas of current and resistance or anything like that? Power, electric potential energy stored in capacitors. All those sorts of things are fair game and useful stuff, I think. I should also mention about this problem here that we didn't quite finish. These directions here are all guesses. The directions for the currents, they're guesses. They may be completely wrong. They may be incorrect. It may be that every one of these currents is the wrong way. I2 might be up. I1 might be to the left. I3 might be, to the left. Who knows? The way that it comes out in the wash is if I solve this problem for the currents, I might find I2 and I1 are negative and I3 is positive. What would that mean? That would mean that I2 actually, the current in this branch actually flows up. The current that flows away from this, the current that flows in this branch actually flows away, it flows to the left. And then if I3 came up positive, then it means we got that one correct. So Zach's asking a question on an RC circuit. Sure thing. We could do an example on that, no problem. Were any of the examples last week on that helpful? Hopefully they were. Let's see. Let me see if I can bring up the lecture note from last week, because there was, I think, a reasonable problem there, and I don't know if everyone had a chance to look at it. Let's see. Unit 4. There we go. RC circuits. Oh, we didn't talk much about household wiring either, but hopefully that was clear. But if it wasn't, let me know, because it's super interesting stuff. Let's see what we got here. So the problem that I had, the example problem that I did, and maybe it was clear, maybe it wasn't, but this idea where I have a battery attached to, let's say I've got a couple of things. I've got a couple of light bulbs. So here's a switch. Okay. And then I have a split here where here's a resistor. And then there's a capacitor. And another resistor. It's like a couple of light bulbs maybe or something like that. And then they're wired together like this. And then this is a voltage V, and let's say this one's R, and this one's R, and this one's C. And at time 0, that's when we do that. We close the switch. And what we talked about last week with that was that when we look at the moment in time, at time 0, we close the switch. And what we know is that the capacitor at that time is uncharged. The charge on the capacitor at time 0, the capacitor at time 0 has 0 charge on it. No coulombs of charge on the capacitor at that moment. So if I were to do a problem, if I were to ask myself, well, how much current flows through, flows in the system at that particular moment? What I would say is we could do a loop rule. And the loop rule would, for each, because there are 2 loops here. And if I want to know, well, how much total current flows out of the battery at the moment when the circuit is closed, I'll say, well, let's analyze the situation here. The way that we'll do it is we'll do it like this. We'll use the loop rule. So if I close this circuit, that's at time 0. At time 0, at t equals 0, how much current is flowing out of the battery at that moment? Okay, so this is what we're going to do. I'm going to say, let's use a loop rule for this first loop right here. Okay, so if I go around this loop, I say I've got plus V. Okay, go through the switch. The switch is just like a wire once I got it closed. And I cross this, let's say I'm pretty sure the current's going to be flowing down, right? So let's say current there is flowing that way. Okay, and that is, I want to know what the total current is. Just to be there. Okay, then this one is minus the current at that moment times R. Okay, and then I've gone around the loop and I'm back to where I started. So there's the loop rule there. Okay, so there's the current that flows through this one. I'll call that one I. Okay, so I'm going to call that I1, I guess. So this one will be I1. This one I'm going to call I2 through the second branch. And from the junction rule, I'll say that this current right here, which is flowing that way, is the total. That's what we're trying to find. What's the total current? Okay, so this one tells us that current number 1 is V over R. Okay, then if I say, well, let's figure out what current 2 is. Well, if I go through the loop here and go through the loop that includes the capacitor, well, we got plus V. How much current is going through how much voltage difference is there between the plates of the capacitor? Well, remember, Q is equal to CV, or C is equal to Q over V, V is equal to Q over C. That's that. The voltage drop across the capacitor at any one moment is whatever charge there is on it divided by its capacitance. At this moment, at time equals 0, Q is 0. So there's no voltage difference here. And then there's a voltage drop across that one. Okay, I see another conceptual question coming up. I'll have a look at that one once we finish this idea. Okay, so this means this has to be 0. That's the loop rule that involves the capacitor, the resistor, and the battery. This also implies that I2 is also V over R, which tells us that the total current is 2V over R. Okay, so because V over R plus V over R is 2V over R. So that at time 0, the total current would be V over R. Now, what about after a really long time? That was the other essence of the example problem. The other one was, well, what about after a really, really long time? After a really long time, the capacitor is full. The capacitor is all the way charged up. Q is equal to C times V. So then V is equal to Q over C. In other words, the voltage across this is equal to the fully charged capacitance. Now, the only way that current flows in this circuit is if current is continuing to build up on the capacitor. after a long time, after an infinite number of seconds have passed, there's no more current flowing through this. So then this loop rule stays the same as it was before, but this loop rule, the one that includes the capacitor, changes. This one is no longer this. The new loop rule for this one will be plus V minus V minus I 2 times R equals 0. Because now, once the capacitor is fully charged, it's equal to whatever the voltage is on the battery. So what does this tell you? The V's cancel out here. It tells us that I2 is 0, just like we expected. The current flowing through this resistor here is 0. All right, so that means the capacitor is fully charged. It's not receiving any more charge on the top plate. What does that mean? It means that the total charge now is just V over R. It's just what's going through here. No more charge passes through this branch of the circuit. No more current. So hopefully that helped, Zach. Let me know what you thought of it. If you want something slightly different, let me know. I'm going to get to the other question that's in the chat right now about this, about other things. But let me know if this one was helpful and useful to you. All right, so the question I'm seeing right now in the chat is, could you do a conceptual question on the topic resistance and temperature, like on the example problem in lecture slides? Okay, so I don't remember exactly what that one was, but what I'll do is I'll erase some of this stuff while I wait for Zach to answer about the whether this question was useful or not to what he wanted to see, and I will talk a little bit about this resistance and temperature idea. Okay, so and it also says, and a problem involving resistivity in terms of microscopic quantities. I'll answer the second question first. I'm not going to be asking you questions about how to calculate resistivities and stuff like that based on microscopic quantities. That is something that is nice and detailed if you're going to be an electrical engineer. I promise you that there will be classes later on that go into this in great detail. But I'm not going to have any questions on this on the exam because I don't think I could pay the kind of attention that we need to really to do that. What I really want to focus on is the practical aspects of circuits. So I'm not too worried about those particular things. So I don't want to say, oh, don't learn it, but I'm going to tell you, don't worry about those individual little things about resistivity in terms of the microscopic quantities like mean free path and average time between collisions and that sort of stuff. That's not going to be a major topic. Thanks, Zach. I'm glad that answered your question. Okay, so back to the first part of that about resistance and temperature, and a conceptual example is something like that. So let's see. So basically the idea is that the resistivity of a substance depends on temperature in this sort of way. The resistivity at some reference temperature times the quantity 1 plus alpha times T minus T0. I'm going to turn that into a bracket so that we have a, don't get too mixed up with all this stuff here. Okay, so just a reminder of sort of how things work here. So what this rho sub 0 here, this is the resistivity at the temperature T0. And rho then is the resistivity at temperature T. So what this is saying is the resistivity changes by a factor of 1 plus alpha, where alpha tells you it's a material dependent quantity that says the resistivity changes in a very specific way for that material. Okay, a positive value for alpha here, and this right here is called the coefficient of the temperature coefficient of resistivity. Now, for a conductor, for conductors like copper and silver and iron and any electrical, aluminum, all conductors have a resistivity a temperature coefficient of resistivity, alpha, that is positive. In other words, as the temperature goes up, the resistivity goes up, and therefore the resistance of an object that has, that resistivity, that material that it's made out of, will go up. If alpha is a negative number, then that means the resistivity will decrease with increasing temperature. Okay, so let's talk a little bit about what materials that are semiconductors have that property. And there's a particular reason for that, and it's a microscopic reason, which maybe gets a little bit towards your second question, which I'll talk very, very briefly about. But basically what happens is, in a semiconductor, as the temperature gets up, the number of electrons per unit volume that can serve as carriers for conduction purposes goes up. It's like they get liberated from their parent atoms. So what happens in a semiconductor is like one atom in a million contributes an electron for conduction. Very rare. And the reason basically is that one electron per million atoms is then free to move inside of the material and conduct electricity. As you increase the temperature, more atoms become ionized. More electrons get promoted to being able to perform conduction duties inside of it. So as the temperature goes up for semiconductors, then you see that the resistivity goes down. So it's opposite. So that's why alpha is negative for semiconductors. For conductors, it's the vibrations that the electrons run into. The atoms are vibrating at higher temperatures. They vibrate over a bigger area, and the electrons are more likely to run into the atoms, and that's why. Okay, all right. Thanks for that, Gustav. All right, so the conceptual example then on resistance and temperature. Well, so let's say that I have a conductor. And let's say that this conductor is in a circuit like this, where I've got a voltage source, and I've got a resistor made out of a conductor, like it's like a wire or something like that. Okay, so this resistor has a resistance that depends on its temperature. Okay, so here's what happens. Let's say the following happens. Let's say that the voltage here, I close a switch in this circuit or something like that. I close the switch and I ask myself, okay, a big current now goes flowing through that resistor, a really big current. And the current is big enough that it causes the temperature of the conductor to heat up. For really low currents, the temperature doesn't grow very big. I mean, it might get slightly warm to the touch, but doesn't get really warm, so the temperature doesn't change all that much. But let's say that when I close the circuit here, I got a really big temperature change. Lots of current flows, and the temperature of this thing goes way up. Okay, the question is, so what happens to the current as that occurs, as the resistor heats up because of the current that's flowing in it? What happens to that current? Okay, so now let's think about what happens. So this is a conceptual happens. What happens to the current? How does I change, if at all? And this is the way you got to think about it. Okay, so for a really big current, I'd say start out with a really big current, because the thing was originally cool, its resistance was, relatively low. Okay, here we go. Resistance goes flying through that thing. Now, what happens though is that current causes this resistor to warm up. Now, if this is a conductor, alpha is positive. So you tell me now, what happens if the temperature goes up? If T goes up, then that implies that the resistance goes up. Okay? So now as the temperature goes up, the resistance goes up. Now, if the resistance goes up, what happens to the current? Remember, V is equal to IR, which means I is equal to V over R. I still got the same voltage applied here. But if my resistance goes up, what happens to the current? Current goes down. So this implies the current goes down. Current decreases. So if the current decreases because of this situation, if the current decreases, what happens to the heating? Less current means less power getting dissipated in that resistor. If the current goes down by some factor here, then the power goes down by some factor. All right, well, that means that this will tend to cool off. And that's the, the temperature just won't keep growing without bound here. The temperature will sort of originally go up, and then it'll sort of find an equilibrium point, for conductors at least. Does that sort of give you like a conceptual thing? Like for a conductor where alpha is positive, if I have a really big current, it means the resistance go up, which drops the current, which has this sort of negative feedback loop where that'll cause the temperature not to grow and get out of hand. Okay, so that's hopefully that gave you a little bit of a sense about how temperature, current, resistance, and all that sort of stuff end up being related to one another. Okay, any other questions? We're sitting at right about an hour right now, and I don't want to take away from folks' time if they want to, get some studying in and stuff like that. But okay, glad it was helpful. Any other questions that I can answer? I'll stay here for as long as you all have questions. So. If you don't have any more questions, just say no more questions or something like that, and just so that I know that folks are feeling like we've had enough. The other thing that I'll ask folks a little bit about is when we get to our last material for the last week, and I'm thinking about doing a review. Okay. I'm thinking about doing a review, and again, I'd like to live stream it, but what I think I want to do is that last Friday, so this would be not this coming Friday, but the following Friday, which would have been our last day of class, week 16, final Friday. What I'm thinking I might doing is at 12:05, when we would have our normal class, just as a tip of the hat to to have each other be able to say goodbye to each other and stuff like that before we have finals. And I'm thinking of having a Zoom meeting, which would be live. I might not be able to record it because those files get really big and it's hard to record things that take a while. But I was thinking we might do a Zoom meeting where people will be here in real time and we could all have we can actually kind of have a visit rather than just a live stream. And I'm not anticipating to necessarily post it. It would just be a sort of a meet and greet, a Q&A that is live only and not available for later view. Just because I don't think that I can record it all and post it as a YouTube video. I'll try and see if I can, but that's what I'm thinking. Would folks be up for that? Does that sound like that's at all useful to folks? Give a thumbs up if you want, or yeah, that sounds good, or something like that. So it would be a week from this Friday. I would schedule a 50-minute Zoom meeting or something like that where we could hang out, ask questions, and decide how this sort of went this last half of the semester at least. Just sort of during our normal class hours from 12:05 to 12:55, but what would have been our normal class time. Just like the good old days before we knew about COVID. Okay, so I'll give that a shot. And what I'll do is I'll post. I think what I would do is post a link in the to announcements or something like that, the Zoom link, so that you could just click on the link and then use the password that I show there or something like that. And we could be live for that. Okay. And we have 20 people or however many folks there are on it that are all sort of have our pictures, we could be live and talking to each other, and that would be useful, a little bit different. I was hoping that this was at least these Q&As were useful, but the lag makes it a little bit uncomfortable, I guess. All right. Well, if there are no further questions, I'm gonna call it here. Unless you have questions you really want me to answer or something like that, feel free to post these last ones. But I will have the exam up in the next hour or so. So look for that then. It's going to be due over the next, you'll have 2 hours like usual to do it. Like we did at least in the last exam. And then so that'll be due Thursday. And then I will have lecture notes posted for Friday along with a short homework assignment so that we can start our material on magnetism. And that'll be our last unit, or the last chapter or two that we do will be over the next couple of days and towards the end of next week. And then we'll have a review session on Friday. Okay? Does that sound good? Okay, well, thank you very much for your attention. I hope this was useful to you. Good luck on your exam this week, and we'll see you next week sometime. Oh, I also do plan on having a live stream next week, a Q&A just on magnetism and stuff like that in the earlier part of the week before we do the Zoom meeting at the end. Okay. So see y'all later. It's been good. Good to have you live here to ask some questions, and I hope it was useful. And have a great week. Stay safe. Stay healthy. Bye for now.